Hi, this is Mr. Yeager, continuing on with the optics unit. Last video, basically we started introducing the idea of how to do a ray diagram, all the pieces of it. For this video, we are now going to go through every possible diagram that you can do with mirrors. Basically, there are 6 different basically situations that you can do with an object in front of the mirror. As long as it's within one of these areas, you're good to go. And basically, it doesn't matter if it ends up being farther away or closer, as long as you are following these particular situations based on where the object is and the type of mirror you have, you can solve for that problem, and you're going to get the same answer every single time, maybe with some slight differences in terms of a calculation. So anyway, let's just get straight to it. We're going to probably go over a couple things just so we make sure we understand. So again, I'm looking at mirrors. So I'm going to switch back and forth between this large table. You might want to copy this table down, pause it, and copy this particular table, because again, this is going to go through every single situation you're going to have to try to deal with. Okay? So again, when you're trying to do these ray diagrams, you draw out basically a coordinate plane where the y-axis, again, is your mirror. Okay, is your mirror. I would usually recommend having this y-axis pushed a little bit farther down, a little bit, so it doesn't have to be completely even. But I'm going to kind of keep it the way it is, since this is actually all measured and scaled out. So we'll just kind of leave it at that. A couple things for a mirror. When we're going to start with concave mirrors. All right. So again, we can draw that on in, but again, we are always going to have that ray of light hit the y-axis and then reflect back. All right. So with a concave mirror, we know that there you have a focal point. Okay. The focal point is where all the light rays are going to come back and converge in between. Double the focal length is the principal axis, C. Okay, so again, I'll write it over here. F is the focal point. All right, and the distance between F and the mirror is the focal length. I'm going to ignore that. I'm going to go ahead and not ignore it, but delete that for now. C stands for the principal axis. All right. And the principal axis is always 2 times the focal length, F being the focal length. All right. Then the last thing we got to just kind of denote real quick is, where will the real light go? Well, the real light, again, this is just going to be an example ray, is going to come in, hit the mirror, and reflect back through the focal point. So therefore, the left side, the side where my light is right now, where the real light is, I'm going to get rid of my ray of light. This is going to be considered the positive DI side, the positive image distance side, while the other side of the mirror is going to be the negative image distance side. Okay, so anything in front of the mirror is going to be considered positive. Anything after the mirror is going to be considered negative. All right. So here we go. We're going to get started now. So going back, what we basically have already figured out is for concave mirrors, the focal length, F, is always going to be positive. The focal length is always going to be positive. And again, I'm going to do another video going over the math, the formula that you're going to use to do some of the calculations for this. All right, so the focal length will always be a positive number for a concave mirror. That's going to be something you're going to have to read out. You're going to have to read very specifically, and we'll do a couple problems where it says the concave mirror, has a focal length of 2 centimeters. You now know that is a positive number. So these are things you're going to have to figure out while reading the problem. All right, so our first situation we're going to look at is when, you can see I have a column for object distance, is when the object distance is greater than the principal axis. All right, is farther than C. All right, that's what we're going to look at first. So I'm going to erase all this stuff. There we go. All right, so I make out my particular my coordinate plane for my mirror. It's again going to be concave, and this is for when the object is greater than C. All right, so I'm going to denote this as F, and this is C. All right, you can do that on the other side too. Some people like to show it on both sides, but you're not going to have any light go on that side, at least yet. All right, so that means when I read the problem, if the object distance is greater than C, that means my object is all the way out here. Okay, it's beyond C is the way I like to usually describe it. It's beyond C. Okay, it's way out there. All right. Again, I know some people get confused. The areas we're going to look at is beyond C, at C, between C and F, at F, and before F. Okay, those are the 5 areas for the concave mirror we're going to look at. We're going to see for convex, we don't have to look at nearly as much. All right, so if I have a concave mirror, I'll go and draw that out again. Okay, concave mirror with my object beyond C. I have to draw my 2 rays. Remember, there are 2 rays involved, and you'll get used to this because I have to do it every single time. The first ray, you always go from the top of the arrow straight to the mirror. And again, the mirror is not the line you might have drawn just to illustrate what type of mirror you have. It's the y-axis. So that ray goes straight towards the mirror and then reflects back through F. All right, back through F. So that's the first one. All right, the second one, the second ray, goes through F, hits the mirror, and then reflects straight back. So again, one goes straight across, parallel, and then back through the focal point, the other one through the focal point, and then straight back. Okay? And so that means the image is created right at the intersection of those 2 reflected rays. Let me go back and write O and I there. So there is my image. My image is right between C and F and is pointed downward, is upside down. And so therefore we can describe it. The way we want to describe it, we have 4 ways to describe this. All right? First off, is it real or virtual? Well, is it created by real reflected light rays? Yes, everything on the left side here is real. The other thing is the image will have a positive image distance, which also means that it is real. So this is a real image. It is inverted. It's going to be diminished. You can tell that this arrow is definitely smaller than the other one, so it is diminished. And then it is between C and F. All right, you can use capital F or little f. I don't distinguish it too much. They both basically are the same to me. So between C and F, that's how we would describe it. So if we go back to your chart, okay, the image distance, basically we're just going to say, okay, we're basically saying where is it. The image is going to be, the VI is going to be less than C but greater than F. The magnification, all right, we'll do it this way. The magnification is, it's going to be inverted and diminished. I'm going to kind of abbreviate here because small boxes. And the image type is going to be real. It's going to be a real image. Okay? So that's our first situation. So our next situation, again, we're going to move along here. What happens when DO equals C? When it's exactly on the principal axis. All right? So what happens if we are on the principal axis? DO equals C. That means now my arrow is right here. O. Okay? I can relabel F and C. All right? And this is still concave. It says, basically what you would read is you would read an object is in front of a concave mirror at a distance of 10 centimeters with a focal length of 5 centimeters. Well, if the focal length is 5 centimeters, that means the principal axis is 10 centimeters, and therefore my object is at the principal axis at C. Okay? So again, you'll get plenty of practice with this with the problems you're going to be doing. Okay? All right? So here we go. We got to do our 2 rays again. What 2 rays? First one, from the top of the object, straight to the mirror. What will it do? Reflect back through F. The concave mirror, it curves towards F. All right? That's our first one. The second one, top of the object through F. Now this one's going to be, I'm hoping this one's going to come out the way I'm planning it. And then it comes back through, straight back. Through F and then straight back. Pretty good, pretty close. This one's always the most difficult to get exactly right. I'm going to cheat a little, well no, I'm pretty good. All right, that image is basically showing up right below C if done correctly. All right, and what I tell students is, if this is what you're expecting, you're going to have to sometimes try to force it a little bit. Okay, this is the way it should work. This is the way it should come out. It should come out at C. This is usually the only one that has issues. It's because you got to be absolutely perfect with your measurements and your arrows and everything. So your image is right at C, so I would say this image is real because, again, it's on the left-hand side, positive VI. All right. It is inverted. Now, this might be tough to see, but it turns out they will be the same size. That one would probably be really tough to be like, is it? Actually, the math will support that. They're going to be exactly the same size, and you would just say you're at C. You're at C. The image distance is at C. So if we go back, when your object is at C, the image distance will equal C. You are inverted, but same size. All right, and then again, it is real. All right, next situation. What if DO is less than C but greater than F? So in between C and F. All right, so C greater than DO, greater than F. Again, still concave. What if that all the wording basically says your object is right in between here? All right, C, F. What do? Same thing, same thing, same thing. Again, I'm hoping that's why this is going to be something I'll be like, okay, I think I'm understanding where we're going. The nice thing is, we do the same thing again. It's going to go straight toward the mirror, back through F. The second one, straight through F, and back. Look at where it's showing up, and that's okay. That's what we're looking for. It's actually going to show up beyond C. Beyond C. Greater than C, if beyond bothers you. Because sometimes people, again, don't like which way. They're saying which way is beyond. All right? So once again, another real image. Another one. All right? Another real image. It is still inverted, so you can see kind of a trend here. It's basically the same two characteristics for at least the first three situations. It is now enlarged, so this is something hopefully you're trying to see a little bit. We'll say DI greater than C. Okay. I hope what you see what's happening. As my object moves closer, my image moves farther away and gets larger. All right. So that is a trend you can use with the concave mirror. As the object is closer, that image should be farther back. All right. That's what we're seeing here. It's getting pushed farther and farther away. All right. Back to your chart. We said DI will be greater than C. It's still inverted, but now it's enlarged. And again, still real. All right. Our next situation, what if the object is at F? What if the object is on the focal length? All right, I guess I'll write capital F. All right. All right. We'll use a little F. We'll be more specific here. All right. What if it's at the focal length? What happens here? All right. What if the object is in front of a concave mirror and at the focal length? So right here now. All right. What are we going to do? Same thing, same thing. Straight toward the mirror and back through the focal length. What does the second ray do? The second ray is supposed to go straight through the focal length first. So what does that mean? All right. Does it ever look like it? Does this second arrow ever look like it's going to hit the mirror? It doesn't. All right. And so now we actually have a very unique situation here. What happens here is, will we ever be able to see this image? Will we ever be able to see where those two reflected rays interact? And the answer is no. So this is a weird situation where we simply have, and we write, there is no image. You draw this out and you go, you can't create an image. It's impossible. Okay? That's just the way it is. And this is, I mean, just kind of a side note, this is actually what magicians use, illusionists use, to try to make things disappear for an audience. They use these mirrors, they understand the focal length behind them, and if they place objects at the focal point, people around it cannot see it. All right, they will not see the reflection. All right, it'll look like it basically disappears because, again, what the magician is trying to make you look at is the mirror image and not actually the object itself. All right, so it basically looks like it disappears. All right, so there is no image. So there's nothing to do really with this one. All right, basically what we do is there's no description. Okay, we can just kind of cross those two out. And I mean, just write no image. There is no image there. Okay? So what happens now if I get in front of F? What if DO is less than F? What if I get it really close? All right? What if DO is less than F? So right up close to it now. All right? Right up close. All right. This is another kind of unique situation. That first line in every single one of our situations is the same. It's going to go straight and then reflect back through. All right? So this is where it gets a little stranger. This is one that I know people struggle with when they do these in my class. This is one that they kind of they have to memorize it a little bit more. Everybody gets so used to doing the same things for everything up to F that this one throws them off. So this is a little bit different. What we actually have to do, so the first ray is normal. The second ray, though, we actually start at F, line it up with the top of the object, and go to the mirror. Okay? So we go from F, top of the object, to mirror. You line up those 3 points. What will happen is that light ray will bounce or reflect backwards. Now, you might be sitting there again and going, wait a minute, these reflected rays will never interact. This is where we get to the idea of sight lines. What happens is we create sight lines that go into the mirror that are created based on the reflected wave. The sight line is based on the reflected ray, not on the incident ray. And it goes through the mirror, okay? Through the mirror on the other side. So we create this straight line from the top reflected ray. What about this one? I basically do a line from the reflected ray on up to the other side. All right? Basically a straight line. And where those two sight lines interact is your image. All right? And so now we get our first virtual image. This is an image that's inside the mirror. So what happens is the image is always created in front of the mirror until you get closer than the focal length. And this is actually how a lot of mirrors are basically made, where they are so large that the focal length is very long and objects generally are always in front of it. That's why they appear in the mirror. Okay? And so this would be a virtual image. All right? When we get to the math, we would have a negative DI. All right? From there, we describe it just like anything else. This one is upright or erect. It is enlarged. And to describe where it is, I either accept negative DI or, basically in the mirror. right? The image will appear within the mirror itself. All right, is what we're looking at there. That's all. We don't get much more detailed than that. All right. So virtual, upright, enlarged, and within the mirror. And again, this is still concave. This is the only situation that we have a unique situation for concave mirrors. All right. So if I go back to my chart, all right, if I'm less than f, all right, basically I'm going to say I have a negative di. That's all I'm going to say. All right. It's in the mirror. It is going to be upright and enlarged, and it's finally a virtual image. So virtual is rare. All right, so that's everything with concave. I mean, this is something while you're doing your homework for mirrors, come back to this. Keep on just looking at it, and obviously eventually try to see if you can understand which one you're going with and being able to do it on your own as well, because you're going to have to do it on the test as well. So the last example is convex. All right, so I'm going to go back to this page real fast. With a convex mirror, we talked about it. The light ray comes in and reflects up and away based on the focal point on the opposite side of the mirror. So this is a negative F. It's on the opposite side. The real light is over here. So this side is positive, the other side is negative. So the focal point for the convex mirror, the focal length, will be negative. All right? Concave is positive, convex is going to be negative. Now, it turns out it doesn't matter where you place the object in front of a convex mirror. Okay? So all we just say is DO has to be greater than 0. It doesn't matter. All right? We don't care whether it shows up beyond C, at C, between C and F, at F, or less than F. It turns out we'll always get an image, so it doesn't matter. There was no exceptions to this. So there's only one situation for convex that we have to understand, one way to draw it. All right? So for convex, all right, we're just saying DO is greater than F. All right? We still want to draw in F and C. The thing is, we want to make sure to draw in F and C on the other side as well. Okay? So the thing is, again, though, it doesn't matter where the object is. You'll place it according to the problem where it's supposed to be, but you're going to be doing the same drawing every single time. And again, this is another kind of tough one, even though it doesn't matter where the object is. Some people have a little bit harder time with this one. So what we do here, okay? I'm going to go and draw in the convex mirror this time to try to help us out. So there's our convex mirror. Okay? What we have this time, okay, is that we do the same thing. We still have that parallel light ray coming straight at this mirror. The thing is, it's going to reflect up and out, not up and away, not down toward F. That's what a concave does. So we need to basically line it up with F on the other side. Okay? And so what we have here, what I actually recommend, is essentially go through to the other side at F. We're actually going to use this because we're going to have to do the sight line. But I still want you to draw the real light. So the light ray comes in. Based on F, it will reflect up and away like this. Okay, based on that line that I just drew going through F on the other side. All right, so that's the first one. The second one, the angled light ray. All right, this one's a little bit tougher to get. What you have to do is you have to line up the top of the object and draw a line all the way to F on the other side. A straight line all the way to F on the other side. The whole point of this is actually not the ray that we're really looking at. We're interested in the ray that's angling in toward the mirror. What we're interested in is where will that hit the mirror. At that point where it hits the mirror, that's where technically the real light reflects back. All right? What happens then is we essentially erase and get rid of the rest of that light ray. Okay? You don't have to. A lot of people actually don't. All right? This section of the light ray is worthless. Okay? Is nothing important. The whole point of it was to help us figure out where we hit the mirror. Because then This is the reflected ray, which I can create a sight line from that reflected ray. Create the sight line going to the other side with that reflected ray. Where those two sight lines match up, that is your image. Okay, that is where your image is. All right, and so for a convex mirror, you will only create virtual images. Actually, most bathroom mirrors are convex. Okay, a lot of bathroom mirrors are convex. All right, it'll always create that virtual image. Now, it doesn't obviously make you that small because, again, we're not referring to that so much. It's closer to a plane mirror. But it is always creating that virtual image. Okay? It is upright. It is diminished. And we'll say it's negative DI. The image is beyond the mirror, in the mirror itself. All right? So one more time, because I know this one confuses people. I drew that parallel ray, lined it up with F on the other side, and then reflected it back upwards. Because again, the real light is all over here. All right? The second one, I lined up at the top of the object and drew a straight line to F on the other side, the focal point on the other side. The whole point, to figure out where it hits the mirror. That light ray would hit the mirror and immediately reflect parallel back. Based on that light, that reflected ray, I can create the sight line on the other side. Where the two sight lines interact, that is where your image is. So to complete your chart, we're going to have a negative DI. It is upright and diminished. I did say it was diminished, right? I didn't say enlarged. I don't know why yeah, diminished. Okay? And it is virtual. It is virtual. All right? So there are all the situations for mirrors. Take some time. Hopefully you pause kind of between each one some, kind of seeing how each one is done. You're going to have to get very good at these. This is going to be a major, major part of the test. All right? So the next video I'll do is I'm going to show you the math. All right? Basically the math that's going to support all of my descriptions as well. All right? Thank you very much.